So I'm very honored and thankful to be invited here and to speak at this event. I've known Alex ever since I started doing mathematics, basically, when I was a graduate student at Yale. So I also consider myself kind of an informal student of Alex, like Martin said yesterday. So, you know, Yale in the early 2000s was a bit of a sleepy place throughout the year. And but suddenly in February, Alex came. And all the graduate students were waiting for this moment to happen. And so we had 2 months where we could suddenly concentrate and listen to go to all his talks. And he was not, Alex was not, well, I mean, was giving all his time, basically. We were sleeping in the office. I don't know how you managed, but this was really a great time. So I'm very thankful. Many of my mathematical the problems that I thought about were inspired by Alex, or just directly given by Alex. So I'm very thankful. I'm also very grateful for the support that he gave me through the years. Okay, so today I'm just going to report about some joint work with Bob Guralnik and Michael Larsen about strongly dense free subgroups. So before I explain the title, I'm going to go back to how it started, what's the motivation, where it came from. And so it, I guess, came from a question of Alex, which has to do with expander graphs. And so this question was, if you start with these two matrices in a SL2Z, and you look at the group they generate. So they generate a finite index subgroup of SL2Z, and you would like to understand the Cayley graph of the finite quotient. So if you look at the finite quotient, or modulo prime, you get SL2Z mod PZ, and using, so it was known that this Cayley graph, when you take these generators, becomes an expander graph, family of expanders. This was based on Selberg's work. But Alex asked, so suppose I remove 2 and I put 3 here, then is it still true? And so this was kind of the set of open problems that we were exposed at in the early 2000s at Yale. Very hard problem. This was solved by Burger and Gamble. So the issue is, if you replace 2 by 3 here, then this group is no longer a lattice in SL2Z, and then the previous techniques using modular forms and so on were not available. So Burger and Gamble showed that if you, as a matter of fact, if you take any subgroup of SL2Z, which is Zariski dense, and suppose that gamma is generated by a finite set, and you look at the Cayley graphs of SL2 Z mod PZ with S modulo P, then you vary the prime, so S is fixed, but you look at its reduction mod P, and this becomes a family of graphs when P is prime. So this family is an expander family. It's a family of expanders, so this means, for example, that the Cheeger constants are bounded away from 0 uniformly independently of P. Okay, so yeah, so this is this is the theorem of Burger and Gamble. So this was around 2005, and so the proof was analytic. The idea was to look at a measure mu. So you look at the measure mu, which is the uniform probability measure on your group, and you look at the convolution powers of this probability measure, and what you need to show is that mu n mod p is very close, becomes very close to the uniform distribution on the finite quotient as soon as n is large enough, and in order to get the spectral gap, you need to show that this happens when n is basically at least log p, which is the minimal speed at which you can reach equidistribution. Because if you're less than log p, then you're not even going to cover the whole group. The diameter of the group is at least log p. So, so this is, yeah, and so it's equivalent. It's equivalent to showing that you have an expander, and to show this. So there were basically three steps in this proof. So, yeah, one of them was this exploiting the high multiplicity of the eigenvalues. There's an idea that appeared in a paper of Peter Sarnak and Shui. And another idea was the classification of proximate subgroups of SL2 Z mod PZ, and this was Helfgott's groundbreaking work at the same time. And then there is a third ingredient, which is what I'm going to talk about, which is an estimate, escape from subgroups estimates. So, so there is a third ingredient, which is this, escape from subgroups. So, okay, what does it mean? It means the following. So you need to show that if you look at all proper algebraic subgroup, H is an algebraic subgroup, and you look at the probability that your random walk hits H at time n, this should decay exponentially fast. Okay, and this is in the big group, in SL2Z. Okay. All right. So this is the escape of mass from subgroup, that subgroups do not charge the measure mu to the n very much, so it's exponentially small. And so this is an ingredient that is necessary here. In the case of SL2Z, this was just followed from Kesten's thesis, which is about random walks on trees. So the thing is, SL2Z is basically a free group, so you're basically having a walk on the free group, and then the probability that you hit a proper algebraic subgroup, so you see the algebraic subgroups of SL2 are basically solvable. So you are looking at the probability that you return into a solvable subgroups of the free group, so only cyclic subgroups are concerned. So this is an easy problem about, random walks on trees. Okay, I have to say something, which is that this estimate, as you see it here, is in fact a consequence of the theorem itself. Okay, so because you can take n to be roughly log p, and you will see that if you have equidistribution in the finite quotient, you must have this estimate. So it's not only an ingredient of the proof, it's actually also a consequence of the proof of the theorem. So it's really important to be able to prove this. And so after Burger and Gambo did their work, people, including myself, we tried to generalize this to a higher rank, and this was done by Ali Reza, Salehi, Golsefidi, and Peter Varyu in a paper in GAFA around a few years later. And one of the key points is to be able to generalize this estimate to a higher rank. So you replace SL2 with G, which is an arbitrary semi-simple Q group, and you'd like to prove a similar estimate here. So yeah, so there are various ways to do this. One is to use random matrix products and the theorem of large deviations estimates. But another way would be to say that, so it would follow, so this estimate here, so this estimate would follows from the following conjecture. That any Zariski dense subgroup of so gamma of G contains a strongly dense free subgroup. Okay, so I'm going to define this now. Yeah. Yeah. So you know the Tietz alternative says that every linear group which is not virtually solvable contains a free subgroup. So in particular here, if you're Zariski dense in a semi-simple algebraic group, you're not virtually solvable, so you contain a free subgroup. It's a bit less known that actually Tietz in his original paper showed that not only you can find a free subgroup, but you can find a Zariski dense free subgroup. So, so here, this is a statement of a similar kind. Strongly dense means that it means that every non-abelian subgroup is dense. Is Zariski dense. Okay, so it's kind of a strong density property that should apply to all subgroups. And it's easy to see why this conjecture should imply this estimate, because if you have this strongly dense free subgroup, then every proper algebraic group will intersect the free subgroup in an abelian group. So you're back in the situation you had in the SL2Z problem. So you're back in a situation where you have a random walk on a tree and you're trying to show that the probability that it hits just a cyclic group is small, and this is well known by basically Kesten 1959 thesis. So this is in fact I was trying to find a name for this notion, and this is due to Alex. So I was in a conversation here in the Einstein Institute, and he told me, well, why don't you call it strongly dense? Lubowski dense. Okay, so yeah, so this is the definition. Okay, yeah. No, it doesn't immediately. So if once you know the Bougain, yeah, once you have the once you have the spectral mode P, then you have escape from subvarieties. Right. But so this is, you need to go mod P for this. Okay, so right, so I'm going to report on the work which is not yet on the archive, but should soon be. What's already on the archive is a previous work of myself, Green, Goralnik, and Tao, and we proved this conjecture. So the answer. So we prove the conjecture for when the case when gamma, when the Zariski-dense subgroup is very large. So it's the entire group of rational points over a field K, which is even a very large field, an uncountable field. So we needed this in order to. So we needed this in characteristic P, and we used it to prove a random version of the Bouguin-Gambaud theorem, which tells you that if you look, so you vary the generating set in a random way, and then we proved that if you take a generating set at random, then it doesn't depend on the field or the prime, but the finite group of Lie type that you get is a uniform expander. So this was necessary in order to apply again the same Bouguin-Gambaud strategy. So so this is one thing. So that we proved, yeah. So we proved this conjecture for this group, right? So we proved that this group contains a strongly dense free subgroup. Okay, and so there will be another paper that will deal with the case when we remove this assumption of uncountable and assume only that the transcendence degree of K is at least 1 in characteristic 0 and at least 2 in characteristic P. So these works. So this method is based on algebraic geometry, degenerations. So it's closer to, if you're familiar with Borel's proof of the Borel-Larsen argument that tells you that every word map is surjective. It's an argument that goes into this direction, but it's not an argument which will help you at all to prove this conjecture for an arbitrary Zariski-dense subgroup. So you need some positive transcendence degree here.
You mean dominant?
Yeah, dominant. So let me state this second theorem, or second part. So we still don't know the answer to the full conjecture, unfortunately. But here's what we can show. So in fact, the conjecture is true for gamma equals G of K, where K is any infinite field. Well, you should not be locally finite, not locally finite field. So it's true for G of Q, for example, but if you really take a genuine, maybe finitely generated Zariski-dense subgroup gamma, then it's true for Zariski-dense subgroups of real algebra, of split or quasi-split real algebraic groups. Okay, so this is the extent of our knowledge, and so for example, it's true for SLDZ. So it's true whenever gamma is Zariski-dense in G over the complex numbers, and if you view this complex numbers group, the complex group, as a real group, then you need to assume that gamma is still Zariski-dense when it's viewed as a real group, and then it's okay. Okay, so if is Zariski-dense over the reals. Okay, and then because then this would be quasi-split. Okay, so here is one case where we don't know. So this proof is based. It's a different method which I will explain in this talk, based on ping pong, so it's based on similar ideas as in Tietze's proof for the Tietze alternative. So, okay, so method is based on ping pong, and the so the method has limits as far as I can tell.
There's no need for uniploidal elements in the group, right?
No, although they will show up at some point in the proof, but no, not in the group, not in gamma. So I don't know if gamma is SON1 of Z. N is at least 4. Then I don't know. Okay. Okay. So I want to relate this conjecture to the Banach-Tarski paradox. So as you know, three subgroups are very closely related to the Banach-Tarski paradox. So let me just recall some definitions. So suppose you have gamma a group. It will soon be a Zariski-Lenz subgroup in a semi-simple algebraic group, but for the moment it's just a group acting on a set. And you say that X is paradoxical with at most R pieces. If you can write X as a union of two disjoint subsets which are equidecomposable with X, with the number of pieces is at most R, and equidecomposable means that you can partition each of these sets as a union of n sets, and same for X, and means that so there exists such a partition, and there exists G1, Gn, some group elements, so that I will take them in gamma, such that Xi is just Gi AI. Okay, so you can, in other words, you can double X by splitting, making a partition of your set X, and rotating the pieces by group element. Okay, so this is called paradoxical, and you count the number of pieces. A small remark: so R must be at least 4. You must have at least 4 pieces, because if you have 3 pieces, then it means that one of them is all of X. You cannot have 3 pieces. Means that one of the partition is the entire thing. So 4 is the minimal. 4 is the minimal number of pieces. So it makes sense to ask when is a set paradoxical, and what is the minimal number of pieces that you can make it paradoxical. And so, for example, anyway. Okay, so the first example that started this whole thing is the case when gamma is SO3R and X is S2. Then I guess Hausdorff, back in the 100 years ago, showed that X is 4 paradoxical. So I don't think he cared so much about 4. Right, yeah, also. So he actually didn't show, he showed that it's paradoxical, but then you can make
I
it
mean,
fall.
should we call the house law
Hausdorff-Banach-Tarski paradox, right. So actually his proof was like this. He took these two elements. So you take two vectors, v and w, you take these rotations of angle pi and 2 pi over 3, and you assume that the cosine of the angle between v and w is not an algebraic number. And then he shows that the group generated by A and B is isomorphic to Zima 2 free product Zima 3. And so he did this just by computing the product. And so, in fact, there is a short proof of this that you can exploit the fact that this is SL2Z, and SL2Z lives in SL2C, and SL2C is isomorphic to SO3C, and then you can use the fact that the trace of a word in A and B is a polynomial in the trace of A, trace of B, trace of AB. This is a very useful fact, and this polynomial has integer coefficients.
By the way, I won't comprehend the word. The great treatment of this in a book by Uspensky.
Uspensky? Yeah, I don't know this book. Yeah. There is a new...
Most of the
of this.
Proving they did a free group.
I see. By the way, there is a new edition of Wagon's book on Banach-Tarski paradox, which is great. So you have this, and so in particular, trace of A is in Q, this in Q. This is, because of this assumption, not in Q bar, but because SL2Z lives in SL2C, you know exactly that the words for which this polynomial is non-zero are exactly the words that do not vanish on this free product. So that's a proof. Anyway, so this is let's go back to to this. So what's the connection between being paradoxical and being strongly dense? I'm getting there. So so here's a fact or a proposition which is due to Decker in the 1960s. It's not very difficult. It says that gamma acts on X is full paradoxical if and only if gamma has a free subgroup F, which acts locally commutatively on X.
How many pieces does output put together on it?
I think something like 6 pieces. If you're not too careful. Yeah. So, what is locally commutative? So this means that the stabilizer of every point in F is abelian. Every x in X. So the point of this point of it is that if you look at the free group itself, free group is full paradoxical on itself, because you can look at so you can partition the free group into the words that starts with A, the words that starts with A inverse, the words that start with B, the words that start with B inverse, and then you're stuck with the identity, and this is basically a source of the problem if you want to reduce the number of pieces. So the trick is to put the identity here together with the negative. So you replace this by FA union the negative powers of A, which you then have to remove from there. And then it's a disjoint union. You have 4 sets, and it's 4 paradoxical in an obvious way. So this is for the free group itself. But it turns out that this argument can be used to show that when the free group acts on a homogeneous on a homogeneous on a set of cosets f modulo the group generated by a fixed cyclic subgroup, then you have the same works. So you can take a transversal, so you can take T times V equals F, and then the partition will be the same partition. You take T intersected with these these elements of the partition, and this gives you a partition of the coset space. And this works whenever you have F modulo an abelian subgroup. So abelian groups, subgroups of the free group are cyclic, so this works. Okay, so that's the idea behind the proof of this proposition. Once you know that the free group or the free group modulo any abelian group is 4 paradoxical, then it's enough to know that you have a free subgroup which acts like this, because then you partition the orbits and you get to partition the whole space, which has only 4 pieces. Okay, so that's it. And now about strongly dense. So this in fact the conjecture is in fact equivalent to the following reformulation. So again, I suppose that gamma G is Zariski dense, and I let X be an algebraic variety on which G acts with no global fixed points. Fixed point. Okay, so
over the algebraic closure.
Yeah, over the algebraic closure. Okay, then gamma acts on X for paradoxical. So this is equivalent, and so this is equivalent because of because you have this. Sorry. Fixed by, there's no point which is, you don't want Gx to be equal to X. Okay. Right. Yeah, so the point is this, that's yeah, actually.
This condition in some way.
Yeah, I believe so. Actually, you can sort of specialize. So, so the point is that you can find finitely many irreducible representations of G. Such that every proper subgroup, proper algebraic subgroup of G fixes a line in one of them. So this is the point. I mean irreducible representation, finite dimensional irreducible representations. So this is not very difficult fact to prove. It's Chavalet's theorem tells you that every proper algebraic group fixes a line in some representation. This tells you can actually find finitely many, and can be irreducible.
We're this number 4.
Right. So, yeah. So then, okay. So then, So if you want to show that every non-abelian subgroup is dense, so if it's not dense, then it will fix a point. Okay. So so this gives you the connection between these two conjectures, right? So. So to show this direction, you can take p to the I. Okay, and the other direction, you take the union of the projective spaces over the various finite dimensional representations.
I still don't see the importance of 4. Why? That was some fixed number.
So 4 is because of this lemma. So okay, you get the abelian. Okay. So yeah, I didn't tell you why 4 implies this. Okay, but once you have 4, then you have 2 transformations. So if you have 4 pieces, then you get only 2 transformations really that are needed to, and these 2 generate a free subgroup, and you can show this locally commutative. Okay, so 10 minutes. So because it's a midrasha, and also because Chen asked me many times, I plan to give you a sketch of the proof for SL3Z. So I think there is just maybe barely enough time, but it should be okay. So so here's a sketch for SL3Z. All right. So for SL3Z, you see that if you have a proper subgroup, then there are 2 possibilities. Either H is contained in a parabolic subgroup. This is a general fact. Or H is reductive. And in the case of SL3Z, this means that if it's reductive, then actually H is basically PGL2 acting on the adjoint representation. So, I mean, the 3-dimensional representation of PGL2. So if it's parabolic, then it means that it fixes a line. Either it fixes a line in the natural module or in its dual. So here we have 3 representations. The natural module, the dual, and the adjoint representation of SL3. And so, yeah, so if you're proper subgroup, then you fix a line in one of them. So the idea is, but you have gamma. Gamma is a Zariski dense subgroup. So the idea is you pick an element A in SL3Z, which is hyperbolic, has nice eigenvalues. So with so eigenvalues lambda 1, lambda 2, lambda 3, which are such that in absolute value they are distinct, like this. So it's possible to do this. Okay, in SL3Z it's easy to build such things. So in general, it's true that it's known that every Zariski dense subgroup contains many such elements called R regular elements. It's a theorem of Prasad and Benoit. But once you're there, the idea is you're going to pick. You're going to pick basically a generic conjugate of A. You're going to try to do ping pong with with that. So pick B, a generic conjugate. So I'm not being very precise what generic means here, but it means that, in fact, there will be a Zariski open set in G such that if you pick an element of gamma inside it, it will work of A. And you play ping pong. So this means that you look at the
So which elements are in gamma?
A and B. A and B belong to gamma. Okay. So you play ping pong. So you look at the projective space of first representation, and you see that there is a north-south dynamics. So they are hyperplanes and they are attractive points. So the matrix A and its powers fix the fixed HA, which is the eigenspace corresponding to lambda 2 and lambda 3, and they also fix VA plus, which is the top eigenspace. And on the projective space, there is this kind of dynamic where the powers of A push everything outside of the bad hyperplane close to this vector. Okay, so we're going to build a free subgroup which will be which will be of that form. So power of A, large power of A, and large power of B. Okay, but you need to make sure that this free subgroup is such that every non-abelian subgroup of it is so cannot fix a line. Okay, so yeah, so this is the picture for one A, and then you have B. So let me just try to draw a better picture. So the thing is, the attracting point of A lies on the bad hyperplane of A inverse. That's a fact of life. So you have this picture, and then you have B here, HB, VB plus, and VA plus, HB inverse. Okay, and so if you're lucky, then these intersection points and the VA plus and the VB plus do not lie on where they are not supposed to lie. So VA plus will not lie on HB or HB inverse. Okay, and then there is a small observation, which is that if you have a word in A and B, which starts with, let's say, some letter X and ends with some letter Y, reduced word. And if this W fixes a point P, pick a point P in your projective space. If this is fixed, then either, so P lies close to either, so either Vx plus or Hy. So if P is not close to Hy, somewhere outside, so this is, for example, if Y is B, if it's outside Hy, then I can play this ping pong game because the first letter is Y, so I'm going next to be sent close to VB plus, and then I'm never going to escape neighborhoods of these attracting points. Okay? So at the end, I will be in the attracting point of X. So P will be close to Vx plus. So this is clear. So if P is a fixed point of W, then W has this special feature. P has this special feature that it's actually close to attracting point of X or repelling neighborhood of Y. Okay. So and then there is a small lemma, which is about subgroups of the free group. So here's the lemma. Suppose you have a subgroup of the free group. It is non-abelian if and only if some conjugate of H contains 3 words, W1, which you can write 3 reduced words, cyclically reduced. W1, W2, and W3, and they have this form. Okay, so this is the lemma. So it's a characterization of non-abelian subgroups of the free groups. It's nothing fantastic. I mean, nothing really surprising, but so there is a nice geometric proof of this using the Stalin's graph, and you just observing that the pi 1 of the Stalin's graph is non-abelian if and only if there is a vertex in the Stalin's graph which is of valency at least 3, and then you get these 3 words. But once you have these 3 words, then it's easy to establish that the stabilizer of that in this situation, so what you need here to show that the stabilizer of P is abelian, you suppose it's not abelian, and you find these words, and you realize that in fact P must lie close to, if it's non-abelian, then P is close to the intersection Hy, Hx, and Hx inverse. But if you're lucky, then this intersection is empty, and so it cannot be. And I say you're lucky because so then you see this may not always be empty, depends on your space. And I'm going to finish on this. So here it works very well for SL3Z because you have V1 and you have V2, and this is just has dimension 2, and so codimension 1. So you have 1, 2, 3. This is codimension 0. So codimension had dimension 0. So you're good. But in general, for higher dimensional irreducible representation, this may not be 0. So you are trying to do the same game, but you're trying to minimize the dimension of H. And so it can be done with the adjoint representation here in the case of SL3. But you have to, instead of taking the top eigenvalue, you need to group them together. So you need to group together the eigenvalues different from 1, and H will be the eigenvalues equal to 1. And this will have dimension 2, and then you're happy. And this way, yeah, you need the splitting. So you need this final lemma. I'll finish on this. You need this technical lemma, which is where actually things happen. That if you let T0 be the set of elements in the maximal torus such that alpha of T is equal to alpha, so this is the -1 of the longest element in the Weil group. So it's a so you have the maximal torus, and you look at the subtorus of the Weil group. Then every irreducible representation of G is T0 good, and this means that you can find a unipotent element such that U sends the fixed points of T fixed points outside of itself. So this is the lemma, and it turns out that this lemma, so you need some transversality condition to hold. So you need at least one element to take this fixed point set outside of itself, and so this lemma works in general, but the proof we have depends on the classification of G. So we have different proof for AN, for G2, and others. Okay, so but this is the thing, and yeah, so with the difficulty in when you're not split or anything is that this, let's say for hyperbolic lattices, is that this hyperplane is huge, very large dimension, and typically it will intersect, so you won't have this. Thank you.